Good afternoon. In today's class, we will be talking about the ripple counters, ripple down counter to be exact. In yesterday's lecture, we saw how we can construct a ripple up counter. So in today's lecture, we will get into the topic of ripple down counter. Then we will talk about some synchronous counters, and in the synchronous counters, I'm planning to talk about the ring counter. Okay, so these are the agendas for today's class, and if time permits, we will get into some other topics as well. So without talking further ado, let's get into the main topic. Okay, so what is a ripple down counter? Can you tell? Ripple down counter, as the name suggests, down counter is a counter that is used for counting downwards. Should I say downwards? Let me give you an example. Say for example, if I want to count from let's say 4, then 3, then 2, and then 1. Can you tell what kind of counter is this in that case? Okay, let's not get confused. Let's write this 1, 2, 3, and 4 like this. Okay, and if you are constructing a counter in this manner, what kind of counter it can be called? It can be called as a up counter. Why is that? Because it is counting the values in the upward direction. On the contrary, this counter is actually counting the values in the downward directions. It is starting with a value of 4, then it is counting downwards, right? 4, 3, 2, 1, like this. But as we are actually dealing with the binary numbers, as we are talking about the digital part, digital electronics, so instead of writing 4, 3, 2, and 1, we should have written it in this manner. Let's say this should be 100, right? Then 11, 10, 0, 1. If 0, then we have to write 0, 0. So let's say if we want to construct this part, this can be called as a down counter. So this is a very basic thing. I don't think you will be facing any trouble constructing this one. Okay, so this notion of down counter is now clear. Now, what are the components that will be needed for constructing this ripple down counter? Can you tell? The components that will be needed is a JK flip-flop. Okay, JK flip-flop. I hope you remember the functionality of a JK flip-flop. If not, I will try to give you a brief idea about that one once again so that you don't get confused. Okay, JK flip-flop. Okay, um, so say for example, if we want to construct a 2-bit down counter, we want to construct this one 2-bit down counter. Okay, if we want to construct a 2-bit down counter, in that case, what should be done? If we want to construct a 2-bit down counter, in that case, what should be done? So this is my question. The answer to this question is, if we want to construct a 2-bit down counter, we will be needing 2 JK flip-flops. Okay, and it has to be connected in certain manner so that the functionality or the principle remains as it is. Okay, and as you can see in a JK flip-flop, there are two things. I shouldn't say things, there are two inputs. One of the input is J, another input is K, right? One input is J, another input is K, and as we all know, the output is denoted with Q and there is another thing called Q bar. Okay, so using this, what will happen? So let me write down the number of combinations, number of possible combinations. So you can say it's a truth table for a JK flip-flop. If you don't forget, and if you haven't, I believe, personally believe that you haven't forgot the truth table of a JK flip-flop, because it's almost similar to the truth table of the SR SR latch, right? So only difference in this truth table is this one, right? You remember that in SR latch, when we provided this inputs 1 and 1 to the from the inputs, we got an invalid condition, but that invalid condition can be eradicated using JK flip-flop. I'm not going to get into the diagram now because I have already described the diagram and its functionality in my previous lecture. If you have doubt in that one, I would suggest you to go back and watch the video once again. In this video, I will only be dealing with the truth tables, the only some basic parts that will be needed for the construction of this ripple counter. Okay, 2-bit down counter, sorry, 2-bit down counter. Okay, so as you all know, when 0 0 is provided as an input, what happens? The output remains 0. Output remains 0, right? If 0 0 is provided through the input, nothing will happen. At that moment, the output remains as it is. What happens when we have 0 1? Do you remember that? What happens when we have a value of 0 and 1? At that case, if you remember, we get 0 here, right? We get 0 here. So I guess there is another thing that has to be incorporated with this JK flip-flop, and that is the clock pulse. When clock pulse is 0 and when the input, there is no input, it can be called as a memory, right? When clock pulse is given but the J input is 0, K input is also 0, instead of writing 0, I think I have wrote it mistakenly. So instead of writing 0, I have to write memory here. Okay, the same goes for the other inputs as well. When clock pulse is working, at that moment only we will get some sort of output. So when we press the K button, at that moment what we get Q equals 0, so Q bar will obviously be 1, right? Why is that? Why Q is 0? Because you can consider this one as set, this one as reset. Okay, when we are pressing the reset button, the output will be 0, obviously. When we are pressing the set button, the output will be high. If output is high, the complemented version of the output should be 0. And this is the most important thing for this one, for this construction part. That is, when we provide 1 and 1 through the J and K, we get a toggled output, right? Toggled or toggle, whatever you call it. So this is the final truth table of a JK flip-flop. And the most important thing you need to remember is this part: when clock pulse is 1, input J is 1, K is 1, at that very moment the output gets toggled. Means whatever the output that was stored previously is being toggled. Okay, fair enough. So now let's get into the construction part. So I hope you remember the construction of a ripple up counter. The construction is almost the same, but I will draw it first, then I will explain its functionality. Okay, so there we will be needing two JK flip-flops. This is my J1, this is K1, this will be my Q1, this is Q1 bar, this will be my Q2, this is Q2 bar. In this case this should be J2, this is K2. Okay, and what, observe carefully, this is high voltage line. This line that I have drawn, it's called the high voltage. High voltage, should I say high voltage, or high input I should say, not high voltage, high input line. So this is connected to J1 as well as K1. Same goes for this one as well. This is connected to J2 and K2, and this Q1 is connected to the clock pulse. Okay, and this clock pulse is connected to the external clock. Fine. So now, do you remember the functionality of a ripple up counter from the previous lecture? Do you remember that? If not, no problem, I will explain its functionality right now. So we have this clock pulse, we have J1, we have K1. Fine, we have clock pulse, we have J1, we have K1, and then what? Some sort of output should be there. So then we have Q1, then we have Q2, right? These things we have. So when we have this, so there will be different, different I guess you are familiar with the rising edge and falling edge, right? The circuit that we are talking about is actually operates during the rising edge. Every rising edge, it operates. When we have clock pulses, it operates, right? So this, as you all know, this J1 and K1, they are always connected to the high input. So we will always be having 1 here, right? So the only difference that this can make is the clock pulse. So when we have a clock pulse of 0, we are using the JK flip-flop. When we are having a clock pulse of 0, let's say we have, let's first write Q2 here, okay, and then write Q1. We are just flipping it out, and I guess this column, even if we remove this column, that is also fine. That's not needed for the time being. So if when the clock pulse is 0, that means we are not providing any sort of clock pulses, so default values will be stored inside of these machines. Usually the default value of a digital devices are zeros, right? We all know this. So what happens during the first clock pulse? When the first clock pulse occurs at the first rising edge, we will have 1 here, right? due to this one we all know that when a JK flip-flop gets all ones, what happens at that moment? It toggles, right? It toggles. So the previous value of previous value of q1, previous value of q1 was what? Can you tell? Previous value of q1 from this table also it is evident that the previous value of q1 was 0. Now after getting this clock pulse, it will toggle, right? It will toggle and it will become 1, right? It will become 1. So after that what will happen? So as I was telling that this flip-flop triggers only when we get a clock pulse of 1 at the rising edge. So when the first rising edge occurs, at the first rising edge occurs, the flip-flop gets the trigger and it toggles the output. Previously the output was q1 was 0, so after toggling the q1 value will become 1. So as we have 1 now, q1 value is 1, so this 1 will travel along this path and it will trigger the second flip-flop as well, and due to this triggering the output of q2 will get toggled. Let's see what is the output stored in q2 right now. The output previously stored was 0, so if it gets toggled it should become 1. Fine, I hope this is understood. Next, in the next clock cycle or second clock cycle, means this one, what will happen at that moment? At the second clock cycle, again we are providing 1 to this flip-flop. That actually means that we are triggering the first flip-flop. Due to this triggering, we will have a q1 value, toggled value of q1. Previously, the q1 value was 1. So if it gets toggled, it should become 0. Now this 0 should travel along this path and it will come to this clock. So as you see that 0 is coming to this clock, or 0 is provided to the clock of the second flip-flop, it won't get triggered this time. 0, due to this 0, it won't get triggered, and as a result the value that was stored before, it will remain as it is. So previously we had a value of 1, still we will have a value of 1. Fine. Then during the third clock cycle, third rising edge, again we are providing a clock pulse of 1. Due to this clock pulse, this flip-flop will be triggered and we will have a toggled output at q1. So at q1 we have 0 now. If it gets toggled, we will have 1. Okay, due to this toggled output. Now this q1 now will travel along this path, and due to this one, the second flip-flop will get triggered and the value stored in q2 previously was 1, but now it will become 0 due to this toggling. So we can write during third clock cycle it is happening. What about the final or fourth clock cycle? At fourth clock cycle, again we are providing a 1 here. Due to this one it will get triggered, and due to this triggering we will have a toggled output at q1. We are talking about fourth clock cycle. So previously we had a value of 1. Now if it gets toggled due to this clock cycle, it will become 0. 0 will travel along this path, and due to this 0, there will not be any kind of triggering to the second flip-flop, so the value that was stored previously in Q2 will remain as it is. The previous value was 0, it will remain as 0. Now if you observe carefully, you can see that the values that we are getting seems like a pattern. First we have 0 0, then we have 1 1 1 0 0 1 0 0. So it can be considered as 3, it can be considered as 2, then we have 1 and then 0, and the series will go like this if we do the triggering using different clock cycles. Okay, so as you can see, in this manner we can build a 2-bit down counter. First it's counting 0, then we are counting in initial state it had a value of 0, so we are counting downwards, because we are counting first we are counting 3, then 2, then 1 0. It goes like this. Okay, so I hope you have understood the functionality of a 2-bit down counter. um, Now we will get into synchronous counter. So now we will get into synchronous counters. So till now we talked about the asynchronous counters. In asynchronous counters, what happens is we provide different clock pulses to different elements. To be exact, or to be precise, I should say, we provide different clock pulses to different flip-flops. But in synchronous counters, we usually provide the same clock pulse to all the flip-flops. So this is the only basic difference between synchronous counter and an asynchronous counter. Okay, so now let's draw the circuit diagram of a synchronous counter. Let's build a 2-bit synchronous counter. So building a 2-bit synchronous counter needs two flip-flops. Those are, this one is a JK flip-flop. This is another JK flip-flop, so it will be my J1, this is K1, it will be J2, and this is K2. Then we will have this Q1, it will be Q1 bar, it will have Q2, then Q2 bar. Okay, now there is a catch. Let's say we have high input or high logic, whatever you call it, it's up to you. This high logic is connected to where? Can you tell? Now this high logic is connected to this and this. Okay, and this line, it is connected like this, in this manner. This is a crucial point here. This is a crucial point, and you need to remember this one. And in between there is a, this is for clock pulse or CP. Okay, so this is the only basic difference, and both the flip-flops are connected to an external common clock pulse like this. Okay, common clock pulse like this. So now what will happen? How will it work? That is a question, right? So now let's try to build a table. We have clock, then we have, what we have here, we have Q2, we have Q1, and so on. And as you all know, we will be dealing with the clock pulses like this. We have clock pulses like this. Okay, so during the first rising edge, a clock pulse comes here, so we will have 1. Another thing you need to remember is this J and K is always connected to high logic, so that means it will always be 1. Always, it will always be 1. Okay, but during the first clock cycle we are providing a clock pulse of 1 to the first flip-flop, we are providing a clock pulse of 1 to this flip-flop as well. Okay, and initially at the very first place, we will have, when no clock pulse is there at the very beginning, what we should have, when no clock pulse was there, we should ideally be having 0 0 here, right? But when the first clock pulse occurs at the first rising edge, 1 goes here, and due to this one, this flip-flop gets triggered, and due to this triggering, we will have what? The toggled output at Q1. Q1 had a value of what? Had a value of 0, but now we will have a value of 1 because of the triggering. Because of the triggering, we will have a toggled output of 1. Now there is a catch. The catch is what will be the value of Q2? What should be the value of Q2? The value of Q2 in this case should be 0. You might be asking that why 0? We are having 1. Due to this one, this Q1 gets triggered. So ideally this value of 1 should travel along this path and this path, right? So all ones should give us a value of Q2 as the toggled value. See, we had previously 0. So aren't we supposed to get 1 at the output? The answer to your question is no. We are not going to get that, because when we are providing the first clock pulse, we have to think in terms of the ready inputs. No kind of, I should say, this kind of traveling is not going to occur at the first clock cycle, second clock cycle, and so on. Whatever the ready inputs we have, according to the ready inputs, we will get the outputs. Okay, this traveling kind of thing is not going to happen during this time. During this rising edge, it will not happen. Maybe after that this traveling will occur. What kind of traveling? I'm saying that due to this one, we are supposed to get a toggled output of Q1 as 1 as well. But due to this one, this one will not travel during this rising edge. It will travel, maybe you can say, for ease of understanding, you can say it will travel along during this time or during the falling edge. You can consider that one as well. Okay, but after first clock cycle, using the ready inputs, we get this one. What will happen in the second clock cycle? So in between the first and the second clock cycle, this value of what? This value of Q1. So now Q1 holds a value of 1, Q2 is 0. What about the second clock cycle now? At this point of time, now we are again providing a clock pulse. Due to this clock, there will be a toggled output, right? There will be a toggled, due to this triggering, there will be a toggled output at Q1. So Q1 previously had a value of 1. Now it will have a value of 0, right? Now it will have a value of 0. What about Q2? Can you tell what will happen to this value? What will happen to this value? This value, can you tell what will happen to Q2? Can you tell? So we had a ready input of, So in between there will be a traveling, right? In between the this q1 will travel along this path. It will come here and here, right? And due to this one, what will happen? There will be a triggering, and due to this trigger, there will be a toggled output. There will be a toggled output. So we had a previous value of 0. Now we will have 1 here. Fine. Then at the third clock cycle, what will happen? At the third clock cycle, again we are providing a value of 1. Due to this one, there will be a trigger at q1. So q1 had a value of 0 previously. Now it will become 1 due to this triggering. And in between the second and the third clock cycle, the q1 had a value of 0. So this 0 will travel along this path, right? Isn't it? Along this path. And due to this 0, as we all know that in the JK flip-flop, if we provide 0 inputs to the JK flip-flop, the value will remain as it is. So it will remain 1 again, right? What will happen at the fourth rising edge? Again we are providing a 1 here. Due to this one, the JK flip-flop gets triggered, and due to this triggering, we will have a toggled output at q1. Previously we had a value of, we are talking about fourth clock cycle. Okay, so due to this triggering, we will have a toggled output at q1. Q1 previously had a value of 1. Now due to this toggling, we will have 0. And in between third and fourth clock cycle, there will be some sort of traveling. What kind of traveling we are talking about? The traveling of the value along this line. So in between this time, okay, q1 had a value of 1. This one will travel along this path and this path, okay, and we are having a clock pulse also. So all ones provided through the inputs of a JK flip-flop. If we are providing ones to the inputs of a JK flip-flop, all ones means it will trigger, right? It will get triggered. So if it gets triggered, it will be providing a toggle value at the output. Previously the output was 1. Now if it gets toggled, it will become 0. So as you can see, there is a pattern. First we had 0 0, then 0 1, this 1 0 1 1. So as you can see, we have built a counter. It's actually counting. It's kind of similar to the up counter, but it's not exactly the same as the ripple up counter. It is called the synchronous counter because we are providing same clock pulses to all the flip-flops. So this is how we can build a synchronous counter using JK flip-flop. I hope you have understood this problem. Now we are going to talk about the ring counter. Okay, ring counter is often called as ring shift counters as well. So it works as a shift counters. We will get into the functionality of this one in a while. So it is built on the principle of D flip-flop. It is used, or it is constructed using D flip-flops. Unlike the previous asynchronous counters, we are using D flip-flop in this case. So as we all know that in D flip-flop, it actually, whatever the input we provide from the input side in a D flip-flop, we get the exact output. So say for example, if we provide 0 at the input, we are supposed to get 0 at the output as well. If we provide 1 at the input side, we are supposed to get 1 at the output as well. So this is how a D flip-flop works. So this is the only thing I shouldn't say this is the only thing. This is the most important thing you should be able to remember. And this attribute will be needed when we will be constructing the ring counter. Okay. So let's try to build a 4-bit ring counter. Okay. Some people call it shift registers as well. So whatever you call it, it's not a problem. So there will be 4 flip-flops, as there are 4 bits, so there will be 4 flip-flops. So these are my 4 flip-flops. Okay, then we have this D1. Here we will be having Q1 bar, D2 Q2 bar, D3 Q3 bar. Then we have D4 Q4 bar. Okay, then we have this clock pulse here, clock pulse, clock pulse. Okay, so as we can see, this clock pulses are connected to clock. Okay, then disconnected in this manner. Okay, disconnected in this manner. So let's try to build a truth table. We will have clock, then we have Q4 Q3 Q2 Q1 and so on. When the clock pulse, let's assume when the clock pulse is 0, at that very point we have 0 0 0 1. Okay, let's say we have this. When clock pulse was 0, we had these values. So if we have these values, let's fill this circuit with these values. Q1 holds a value of 1. Okay, Q2 holds a value of 0, Q3 0, Q4 0. Okay, this is what we are assuming. When clock pulse is 0, these are my values. Then if we have a clock pulse of 1, what will happen at that case? At that point in time, there will be some sort of shifting. This is this is a little bit tricky thing, but you have to understand this part. When there is a clock pulse, which clock pulse we are talking about? We are talking about this kind of clock pulses. Okay, when a rising edge occurs at that point of time, in this shift ring counter, some sort of shifting will be done. So this 0 will travel along this line, it will come here. Okay, just before the clock pulse occurs, fraction of a second before the clock pulse occurs, let's say there is a sort of traveling here, it travels along this path just a fraction of a second before this clock pulse occurs. Due to this 0, what will happen? Due to this 0, we will have a Q1 value of 0. Why is that? Because we told you that whatever the input to the D flip-flop, we are supposed to get the same value at the output. We know this, right? So this is what we are doing. we have 0 at the input side, so ideally we will have q1 as 0 as well, isn't it? So let's cross this one, and we will be having 0 here, so that's why we have filled q1 as 0. Now this one, the previous one, will travel here, it comes here, right? Isn't it? Due to this one, we will have what? We will have 1 here, right, at the output. So q2 becomes 1. This 0 travels along this path, it comes here. Due to this 0, we will have 0 here at the output. So this 0, if we want to write, that's also fine. Let's cross it out, so it makes it difficult, easier for understanding. 0, and this 0 travels along this path, comes here due to this 0. Okay, so let's write q3 as 0, and due to this 0 we are supposed to get a 0 here. Okay, and this 0 now goes here, and now it will travel during the third clock cycle, or you can say just a fraction of a second before, or if you, even if you say when clock pulse occurs, that is also fine, it's up to you. This is just for your understanding, nothing else. So this 0 travels here, it comes here. Due to this 0, we will have what? 0. Due to this 0, we will have, let's cross this 0. Due to this 0, we will have 0, and this 0 will travel along this path, it will come here. So we have a q1 value of, I forgot to write down this 0 previously, so it's about the second clock cycle. So due to this 0, we have a q1 value of 0. Due to this 0, we will have a q2 value of 0, and this 1 will travel here, it will go here. Okay, so let's write q2 as 0, and due to this 1, we will have 1 here, and this 0 will travel here. So let's write q3 as 1. Due to this 0, we will have 0 here, and this 0 will travel in this place. So we have q4 value as 0. What will happen at the third rising edge? What will happen now? Can you tell? At the third rising edge, this 0 will travel again here, isn't it? Due to this 0, we will have 0 here, q1. This 0 travels along this path, comes here, isn't it? Due to this 0, we will have 0 here again in q2. q2 becomes 0. So q2 previously had, now the previous 0 comes here, isn't it? And due to this 0, q3 becomes 0, and previous 1 travels along this path. Due to this 1, this q4 becomes 1, right? q4 becomes 1, and it goes like this. Okay, so if you observe, you can see that it is actually shifting, some sort of shifting is being done. First, at the, when the clock pulse value was 0, we had 0 0 0 1. When the clock pulse value was 1, we have 10, that is equivalent to 2 in decimal. When the second clock pulse occurs, then we have 100. Should I say 100? Even if I say that, that's also fine. Otherwise, in this manner you can understand. You see, the 1 is traveling along these diagonal values. You see, first we had a q1 value of 1, then this we have in the this when first clock cycle occurs, we have q1 as q2 as 1, then we have q3 as 1, then we have q4 as 1, all other values are 0. So in this manner, as you can see, we are able to build a ring counter. Okay, so I will give you one task, and that task is to find out what happens when the clock cycle number increases. I have shown you what happens when we have clock 0, clock 1, first clock cycle, second clock cycle, third clock cycle. Your task is to figure out what actually happens when the clock cycle number is 4, 5, 6, 7, and so on. At least try to figure out what is actually happening here. Okay, now I will consider this as a class work. Try to do it on your own, and meanwhile I will give you some other topics or other problems in your WeChat group as well. Try to solve this one, write it on paper, and if you encounter any difficulty, feel free to let me know. Okay, you have 10 minutes to solve this question. We will get back to you once this thing is sorted out. Okay.